week number 10, lecture 8. Right? So today we are going to cover chapter 12 or ARE. Okay? This is to prepare us for the next chapter on H2 optimal control. And many of you probably know that H2, okay, is more generalized setting than what we learn about LQR, okay? LQR. So today we are going to start with LQR, and so then we just try to understand two things. One is called finite time, one is called infinite time, okay? LQR. So this one will lead us to record differential equation. This will record to algebraic recursion equation. Okay. So with that, we are going to focus on this ARE part, and we are going to see some of these important results. After that, we are going to ready to do H2 infinity control. In fact, this is like less than 10 slides. So, in fact, in one way or another, you probably heard about this. Okay, you heard about this. So basically, we are going to add contents in here. Okay, in here about 30 minutes. Then we focus on ARE abstraction. Then with ARE prepared, we can do H2. Okay. So again, this H2 will be based on x dot is ax plus b1 u and b2 b11 b12 w. Okay. And we have a y is actually the z in the middle. Okay. Z is like C, okay, 11x plus D11u and D12u w. And we have y is written as C21x plus D21u and plus D22u w. So you can see we have a dedicated control input in here. This is my performance. So these are different, okay? So we have equation like that. So we discuss H2 in this format, okay, in this format. So in this format, you are going to see very clearly about you have a control U here, you have W in here, okay? So you have a Z in here, you have Y in here. This as K, so you design how giving a nominal plan, how you can design that, okay, how you design that. So that's the kind of nominal design, okay. So in the end, basically I want my TZW to norm, okay, to norm, like minimize. So you minimize subject to K, okay. So, but you can see this type of formulation, okay, this type of formulation is more advanced, generalized version of classical. So this is kind of like classical H2 type, special cases of class H2. Okay, so this today, this week, basically, we are going to do H2 infinity as well, get started. So that's the next one. We talk about TZW. Actually, we can say J omega in here. So, okay. So you have a realization. You can always do this, and you minimize this one, and you have K. So this is actually infinity control, right? Okay. So. This week and next week, we are going to focus on this chapter 12, 13, and 14, okay? 14. So again, these are the techniques you need to learn for the nominal control synthesis. So it's for nominal control, nominal optimal controller synthesis. Okay. So you can say, oh, I do H2, H infinity, and of course, before that, we already learned something called what? Mu norm, right? Mu norm. Okay. But the mu norm has a issue regarding existence of the controller. That decay iteration may not always exist. Okay. It's a synthesis method. So all these are the synthesis methods. So then you can propose many others, or some people talking about mixed norm, okay? Mixed norm. So like H2, H infinity, mixed norm. So that's the next step we're going to talk about it. But these are the foundations you should know, okay? You should know. Let's take a look of this finite time state regulated problem for the LTI system. So it's very easy. The LTI, A is a constant, B is a constant, they're all perfect and known. You know in the initial condition. So where's the optimal control problem? Basically, what you can do in here, you cannot change A, cannot change B, but you can change U, right? This is giving. So you can change the U in here such that, because if you have different U, you have different X. X is got Siri cut in and try to give us some thought I'm going to buy some mattresses. So. Okay, let's continue. Siri is bad, it's naughty. Okay, so here A, B, so then you know that the J is a function of U, so basically we are talking about not a controller, be careful. I'm not using a controller, we are talking about control signal. Okay, we're talking about signal. We're not talking about control load yet. Okay, it's not a load, it's a signal. So everything is fixed, okay, so it's finite time or fixed time, final time, terminal time. And we don't care about what will happen to the XTF. It's called free terminal state. And we assume that the U is constrained like in here. So the Q and R are semi-positive definite. Okay, positive definite. It's kind of energy. Okay, kind of energy. Okay. So in this case, regarding a Pontryagin minimum principle, you can learn about Pontryagin maximum principle, minimum principle is okay. So here are a few slides from this website. Did a very good job. So basically, in general, we're writing something like that. You have a state space. We had actually not a state space, but a nonlinear space. LTI system. This is more general, right? So it's the same. You have a control system. You have a control in a set. So then you have admissible control. Then you have a function. X and UT and integral, so this is the cost. So this is terminal cost related to the capital T. So then 0 to capital T, you have cost, you have terminal cost. Remember, in our LQR, we didn't put the terminal cost. It's a free terminal, okay? Free terminal. So this is the original initial value problem. Given x0, we have x dot. So this is called general Bose form, okay? This is a typical OCP, optimal control problem. The job is to find out the optimal control signal. I keep saying signal, it's not law yet, okay? Signal. Now how to do that? So basically, Pontryagin maximum principle says that let's assume this is a value set. So this is V, is all everything. And assuming that for all the feasible control law in here, then this is the maximum value, and set that maximum value is Vxt. We no longer have the U because it's a maximum. Okay, all those maximums. Okay, so we start Vx. Okay, partial V partial x, and you have a x dot. Okay. Remember? Okay. So this is nothing but what? That's v dot. V dot is partial u, partial v, partial x, and x dot. X dot is fx. Fx is original, your dynamics. So this is basically v dot. V dot plus original f, and construct something called Hamiltonian. Okay. With this Hamiltonian, it is a function of x, u, vx. Okay. In fact, if we assume this thing is a Lagrangian, okay, it's like a Lagrangian lambda. So then we write x, u, lambda, t. Okay. So this is clear. So clearly, because we are talking about at the maximum part, so therefore I checked all this maximum. Okay, a maximum. I know that it must be zero. It must be zero. Okay, because it's peak point. Okay. So based on that, this is actually called HJB equation, Hamilton-Jacobi-Bellman equation, and this is very straightforward. Okay, very straightforward. Therefore, based on that, you know that is a partial h, partial lambda is x dot, and then the lambda dot is minus h, partial x. So this is called, actually this is called state equation. Okay, state equation. Because you do partial lambda, you have f left only. Okay, so this is f. So this is a state equation, initial condition, and this is called canonic system of equation. This one is called lambda dynamics. Is called co-state equation or adjoint. Okay, adjoint or co-state equation. So then lambda capital T is already given. It's a partial s, partial x, and they have xt here. So this, if it is free terminal, then s should be zero. Okay, this guy should be zero. So lambda t should be zero if it is free terminal. Okay. So I think this is just a quick review of Pontryagin Maximum Principle. The key point is here at this point. Okay, and this corresponding to this separate state equation and co-state equation. And it's very interesting that x is an initial value problem, and it's a ODE with initial value, and this is also ODE, but it's a final value. Okay, so it's kind of like what? You have a if you put x and a lambda as a vector, then you have a ODE, right? This ODE, half of the ODE variables, vector variables, initial value, and then the other half is final value. These are specified. So what are you going to do? This is called TPBVP. Okay. TPBVP. It's called 2-point boundary value problem. Okay, 2-point boundary value problem. So in here, you basically have vector ODE. You have x and a lambda ODE, but this ODE has half of initial value and this boundary value. So it's called TPBVP problem. So, and of course there are existence issues and numeric issues how to solve this. So in our LTI system, okay, we construct like what they said is this one. So this is my f, okay, this is my f, and this is a lambda. This is a x dot is x plus bu, okay. So this is Hamiltonian. Then you do partial h, partial u should be zero. Then you have r, u, and b lambda. Okay. So in this case, you will see that this u, best u, will be inverse minus r inverse b lambda. So if you get my lambda, I know what is my u. So here we are no longer talking about what? Control signal. We're now talking about control law. There's a law. Okay, there's a law. So this is the law. Okay, but previously it's a control signal, but somehow because of the Pontryagin Maximum Principle, you are coming out a law. So this lambda. So and also this always minimizes h. So because this second partial is greater than zero, which is all good. So then it's not a state feedback. It's lambda. Okay, it's not lambda. So if we can know lambda, we can construct a u, right? That would be great. Okay, that would be great.
What will the DEA of
B is
okay, this is
A, B, C, D.
okay.
So, but we don't know what is lambda. Let's assume, okay, here's some. Don't ask me why you assumed this. Because we really want to know my state feedback. It would be nice if I have a state feedback, right? So that's why we produce a PT times XT. We assume lambda T is PET XT. This is purely assumption, okay? With to see what will happen about P, okay? The P is nothing but a time varying what? Gain, right? Time varying gain plus time this one, then this is my negative feedback, right? So my LQR problem will be solved. So initially I solve the U star is my optimal signal. Then in the end I find out there's a feedback structure that can automatically make everything nice. That would be nice. So this was not discovered until in the 50s, 60s. So by I think it's due to LQR is due to Karman. Okay, so until here we try to figure out what is the P. Okay, what is the P? So let's do a lambda dot or a P dot X dot X. So this is true. It's very easy. On the other hand, remember, I have a lambda dot is my partial H partial X, right? Is negative partial H. So then this is my X dot AX. This is my control signal in here, but I don't have the lambda. This is the co-state. But I probably can put because lambda is Px, so I just with this P in here. So I have all the stuff in here, and if I know the PT, that would be great. However, from here, I know lambda dot is minus QXA lambda T. Why do we say that? Lambda dot, okay? So lambda dot is actually end up with XT like this, okay? Like this. So in the end, we have something very compact and times X equals 0. Okay, let me go back a little bit. So you know that lambda dot is partial H partial X. Okay, what is a partial H partial X? Let me do. Partial H partial X is XQ, right? Okay. Partial X partial H partial X nothing is 0. Okay, but there partial H partial X is lambda A, right? Partial X partial H partial X, this is 0. Okay. So what's left is there are two terms. It's here. Minus QX minus A lambda. Okay. Let me go back one more time. Minus, because it's a lambda dot. Okay, I'm here. Lambda dot is minus HX partial X. So my lambda dot here will get minus QX and minus A lambda. QX minus. If you don't feel this comfortable, go back. Do partial here, you have minus QX and minus lambda A. And because of the vector operation, you need a transpose. So just be careful about this. Okay. So from here, you know X dot is related to X like this. Lambda dot is related like that. What you should do? Okay. What you should do? Okay. So you use this guy, put this side. Okay. Put this side. Okay. And use this X dot with this side. Put this one. So you always have X left over, and everything else is in here. So it's very interesting. So it's a P dot, PB, R inverse P, B transpose P, and PAAP, and Q. Okay, some structure there. We remember the Lyapunov function. Okay, Lyapunov equation. So this is called matrix type of Riccati equation. The reason is this one equals to 0. Then, because xt can be anything, so that one has to be 0. Okay? So this one has to be 0. So this equation is, this equation is called RDE, Riccati differential equation. So in this case, we derive this one is because XTF is free terminal. So we can move everything this side. So we write P dot always like that. So lambda TF is 0 because of free terminal. So the TP-PVP problem, boundary value. So another boundary is all lambda TF is 0. Okay? So there's three properties of this P. So this is a matrix Riccati differential equation. Riccati differential equation. Okay? Matrix Riccati differential equation. And we also understand that the boundary condition of this one is PTF is 0. PTF must be 0, okay? So you can see you have ODE like this. This is ODE, ordinary differential equation, but you don't have an initial value specified, right? You have a final value specified. When t goes to infinity, this guy goes to 0. Okay? So three properties. In this equation, if AB system are controllable, okay? So you always have PT existing and unique. This is important. PT times XT, okay? So that's a key step. I write lambda t is PT XT. So it's a key step we can construct a negative feedback control to achieve LQR, linear quadratic minimization of the J. But when we can write down? So it's always existing, okay, and unique. It's very beautiful. And it should be symmetric, okay, symmetric. And of course we have R is the weight on the control, Q is the weighting matrix for state X. That's semi-positive definite. So this PT is also semi-positive definite. So if both of them are positive definite, then PT is also positive definite in this finite time window. So this is great. This is great. So this is already, so you can see that in the end, what I can do is to write a negative feedback control law, which is optimal. That's significant. Did you know that? Now we take it for granted, but initially we leave only on U star. That's optimal signal. You have to compute the signal and store in the memory, right? It's very huge lookup table from T0 to TF. You need to build that. And at that time in the 60s, storing that U star T is unbelievably hard, right? It's very expensive using a magnetic drum circle to do that. So if we can construct this type of thing, everybody's celebrating. Okay, so people put in the study of this RDE and solve the P, so you can make it a closed loop like that. In the end, U star is a state feedback control with time-varying gain. The reason we have time-varying gain is because of finite T sub F is finite. Okay, so remember, because we have TF, finite time is finite. Finite time is finite, so the gain is time-varying. And this is optimal control law. This is for finite time. So in the end, you can construct a feedback controller like that. State, feedback, then the overall thing will make your J optimal. Isn't this beautiful? Yes.
So before this, people used to solve the optimal control
Signal.
problem and find the signal,
Yes.
right? And there's,
Yes.
I mean, I'm not with.
And Pontryagin only offer you signal.
Yeah.
You can get the U star. I don't know, U star is a function of X, you know.
Yeah.
That's the later development. Well, that's why LQR still has an important role in control theory. So that we can write a controller or feedback controller like that, yet achieving the optimal performance J. Okay, and beautifully, this J written in this way, using that controller, and the smallest J is decided by the controller U star and T naught. Okay, And U star is already written in this time varying gain KT, okay? And J star here is written as PT0, and these are the initial states. Beautiful. Beautiful. Okay? So that part is very quick. So the reason we have this beautiful result can be written in this time varying closed loop is because of thanks to what? Pontryagin Maximum Principle. Now, we are talking about infinite time. So this is an example of finite time interval. I'm going to skip this one. It's just very involved. Okay. So let's talk about infinite. Okay. So again, the finite time LQR results in the time varying gain matrix KT, not convenient in application. K needs to be stored in a very large lookup table, perhaps. So ideally, we need to talk about when this TF is big enough. It's very big.
So, for the case of finite time LQR, we always assumed the free terminal.
Yes, we are still assuming this is a free terminal.
Yeah, but for the finite time, can we do? I mean,
yes, you can
we do LQR with
yes.
terminal cluster?
Yes, yes. That is a dedicated topic, but it's already standard in the literature. Okay, that terminal cost will be the final value of the lambda TF. Okay. All right. So we start from here. So everything is right here, and we also have this one. So we do LQR, linear quadratic regulator. But interestingly, here we also have Q and R here. So it's the weight matrices. These are giving symmetric, positive, symmetric. So this is basically what's the difference is here is infinite. And the infinite LQR will give us something we will send TF to infinity. So this is a finite. This is finite. In the finite case, we know this will go to like this. But what is this PT? What is this PT? Okay. And again, we go to here and seek the PT. Basically, we want to solve the PT. We know that the TF is 0. TF is 0. Okay. And we want to solve this P. Okay. But if the system is fully controllable, we know that the PT will converge. Okay. It's stable, converge to P bar. Then we send this P dot is 0, okay? P dot is 0. So we know the Pij will go to 0, okay? Go to 0. So in the end, when T goes to infinity, the Riccati differential equation will reduce to algebraic Riccati equation, P bar, okay? The P bar. P bar. So in this case, everything you send TF in the infinity. So the P bar, this is P bar, this is P bar. So in the end, you will discover that instead of time varying gain, so it's a state feedback with constant gain for LQR. If your cost TF is big enough, then you should use K as a constant. Okay. So that's another beautiful side. You don't have to store all time, all K. You just have one K stored there, and you can use static. It's for static time invariant gain of negative feedback. And again, it's very beautiful. Everything is the same here, P bar. And how you solve this equation, this one, this is called algebraic equation because we don't have P dot. We don't have P dot. Okay. So in the end, you are going to see that x infinity is 0. X infinity is 0 because we assume that our equilibrium point is the origin. So this one, x0, no matter how far away from 0, then it will make x infinity to 0. Okay. Okay. That's very important. So, but if you have a bias, so if this is not 0, then you integrate this one will what? Your energy will add up. You have a constant values in here add up to infinity. So that's not true. If it is not the case, then J is infinity. Okay? So then the overall system closed loop has to be asymptotically stable or exponentially stable. If not, then something will be wrong. It's infinity. So in other thing is this is the final cost. It must be finite because it's a minimum. So then it's contradiction. So this picture is the same as before, but this is not bracket T anymore. And how to solve the K? Just this is my B times K. So this is K. K is a minus R inverse B P bar. Okay. So finite time and infinite time, very big R. So this is an example to show you how to solve it. So let's skip that. So in the end, you have the feedback like that. You also can introduce, because we are using a battery. Small. So we need a battery. Okay. So you can see this is the feedback. Okay, this is the feedback. If the question is, we need this type of full state feedback. Can you see? We need X available. Okay. But what if I don't have it available? Okay. Then you need to reconstruct. So this is, everybody knows. This is called observer based. This is called observer based. Okay. Before we move to our real ARE slides, I want to show you this one thing. This will be quick. So this is state. This is observer. This is observer. So you construct X hat. Okay. Z is this ZT is the same as my X. Okay. Then minus KX. So this is observer to reconstruct the internal state. There is a tuning knob about G in here. Okay. About G. This tuning knob is my observer gain. Okay. That can define observer is fast or slow. Okay. And K and G, yeah, should be carefully designed. I want to show you something you haven't heard before. Here is called prescribed margin. So remember that if we in a pole placement, okay, in a pole placement. So this is real. This is imaginary. So if you have a pose in here, or pose in here, okay. But you say that, because of some reason, I want you to put all my pose inside. So this is something called alpha. So I want you to be minus alpha all further down. Okay? Don't put anything in this. So this is called prescribed region. Prescribed margin. Okay, margin. How you can design the state space feedback design such that the pose will guarantee not within this strip. How you can make sure? Guarantee is this side. So this is minus alpha. This is 0. Okay, this is minus alpha. Okay? Minus alpha 0J. Then it is interesting. Okay, it's interesting. It actually amounts to what? It amounts to you put e to the power of 2 alpha t here. Can you see it? You just weight it and exponentially weight it. okay? Then you have minus alpha this side, okay? So basically you have LQR, right? If you say, oh, I want all my roots on the left minus alpha, okay? So you should put e to the power of 2 alpha t, okay? So 2 alpha t, you see that? Okay. 2 alpha t. So then, how we can do that? So what they did is to make this one, e to the power of alpha t, x e to the power of the u. So you basically to do exponential scaling of every signal, okay? So then you can achieve that. So then here you put a plus alpha. Here you solve the p alpha. Then you have a state feedback guarantee is true. Let's see an example, okay? So suppose you have a double integrated system like this. So you want to do LQR, and you want to have a control, make sure all the closed loop poles on the -1. And left is smaller than -1. What we do is to do transformation, okay? Then we have this system, original system. So in this system, you will see that there is a full rank, observable, controllable, and observable, controllable. Then you put the e to the power of 2t in here. Then you do this, you can choose your q and r, doesn't matter. Then in the end, you solve the PR, okay? So this is my feedback. So this is the ARE, you can solve it. So after you solve that, these are just straightforward derivation, okay? So you solve that, the closed loop system will be like this. And then we know that this real part of the roots will be always -1. Okay, -1. So this is a guarantee. So in summary, what we have just gone through is Pontryagin Maximum Principle with some major conclusions. We haven't proved it. Finite time LQR, infinite time LQR, talk about algebraic Riccati equation, talk about full state infinite time LQR is static negative feedback. We can also introduce observers to do that. And we talk about prescribed stability margin issue. So you basically scale all the signal up to e to the power of alpha t. The reason we have 2 alpha t is because of square, okay? And we can talk about output infinite time LQR because we can using output signal to construct, which is the same, not full state feedback, it's output feedback. But you need to have a observability condition. So to make the observer have an estimation of the x hat. So all these are just a simple, quick overview of LQR from finite time to infinite time.
Some questions, sir. If first of all, in this case, that's what we see here. The object. I mean, we don't have any constraints on control input. We don't have any constraints on states and no terminal cost condition. You said that we can add the terminal cost to LQR, but can LQR? I mean, I haven't studied it, but could it also handle constraints on control and
very good question.
Control input?
Answer is no.
No.
No. They cannot do. LQR cannot handle the constraints so far. You need some very special handling. However, Pontryagin Maximum Principle works for all situations. Okay.
Yeah, because I wanted to see then what is the advantage of MPC to this, and I think then handling the constraints is gonna be.
That's the major point. Yes. So if you say, oh, PID is good, but can PID handle the constraints? It cannot explicitly do it. Only MPC can do it. LQR, LQG, no. Okay. You cannot explicitly handle that.
Maybe also only for linear systems, but MPC you can do for nonlinear systems. I mean, you can use nonlinear models.
Yes. However, LQR and LQG later, they give us better understanding and insights into the optimal control. Okay. Like what I said, optimal control signal versus optimal control law. That part of, when I was a student, I'm very confused. So I feel I should make you guys aware the difference. U star versus control law. And especially, you can do a feedback law, so it's great. In fact, I have more slides on this, but I think it's enough to talk about it today. So here are the slides. I hope I can go through with you in the next 30 minutes. So now if I say ARE, you will feel very comfortable, okay? Otherwise you feel like, where this is from, you know, I lost context. So, yes, so we have, we use a P, but here we use X, okay? So this is our, this is R and Q are the weighting matrices. Like in R is for control, Q is for state. So they are symmetric, okay? Complex conjugate. So of course, ARE may have many solutions. However, we're only interested in symmetric solutions. Okay, we're interested in a symmetric solution that ARX is stable. So the solution is called a stabilizing solution. So the solution may not be unique. Okay, may not be unique. Okay. So RX is stable. Okay, it's stable. This RX reminds you the state feedback. Okay. Yes. So we only consider this is a stable solution for stabilizing solution for this ARE. Okay. It is from the infinite LQR solution. Okay. So the Hamiltonian is like this, Hamiltonian, okay, like this. And if you do Hamiltonian, if you do this similarity transform, you are going to convert to this. So in other words, they are similar. This one and minus H transverse complex conjugate are similar. Okay. So if lambda is the eigenvalue of this guy, then you know that the minus lambda star is also eigenvalue. Okay, so that's a quite beautiful property of Hamiltonian matrix. Also, we conclude that the eigenvalue of this H, okay, is not in the j omega axis. Okay, purely imaginary. Okay, this is called purely imaginary. Okay, so that's also very important property. So if you have a system, you have a LQR problem with Q and R, and you write A, R, and minus Q minus A transverse, construct a Hamiltonian matrix. So this matrix has a very, very special properties. One is a kind of anti-symmetric. Another one is called all eigenvalues not on the imaginary axis. And half of them are in the left half plane and another half in the right half plane. So you have 2n eigenvalues, okay? This is a 2n by 2n matrix, right? So in this case, it's interesting to split the solution X into two parts, okay? Into two parts. So the X, okay? N-dimensional spectrum subspace corresponding to eigenvalue less than 0 is X minus here and X plus, okay? Again, this is a 2n by 2n space, okay? So they define something called Riccati operator here, Riccati operator here. So the just do when S is all the subspace is corresponding to the stable side, left half plane, then it's called X minus H. Then you can write down in the X1 and X2 subspaces. Okay. So the X, okay, in AN can be written in the X2 and X1 inverse. Okay. So of course, H has no eigenvalue on the imaginary axis, and these two blocks are opposite. One is left half plane, one is the right half plane. Okay. So when you construct this H here, like we did in here, so giving A, B, C, giving A, B, it's full state feedback, giving A, B, giving QR, you can get the state feedback matrix P. So then it's a minus R inverse B transverse P will get you a like K constant for the state feedback. Okay. So it turns out that constructing this Hamiltonian matrix H, very special structure, we will be able to get X1 and X2 out of it. Okay. And then the solution, remember, the solution actually we are talking about this solution. Okay. We just write the solution X is X2, X1 inverse. Okay. X1 inverse. So that derivation is actually very straightforward. There isn't a lot of things to get involved. All the thing here is compact notation. Okay, compact notation. Due to the introduction of this special form of H matrix, Hamiltonian matrix. But if you feel like, oh, why I write Hamiltonian matrix like that, so that will go back to this reason. Okay? The reason is in this slide. Remember, we introduced Hamiltonian matrix. Do you remember the Hamiltonian we introduced in here? It is in here. So here, okay, here, we know that partial H, partial U should be 0, so U should be like this, and partial U, partial X should be positive, definitely like that. So this, if we write it in a matrix format, like X transpose Hamiltonian matrix, so it will be in the same format like this. Okay. Don't feel very surprised. So this format, okay, this format. The reason this is the format. So let's go through these conclusions. So if you construct Riccati ARE like this, okay, and I know that the solution must be real and symmetric, and the A plus Rx must be stable. There is some proof to show that this is true. Okay? And the proof is true. And we assume that the eigenvalues of this Hamiltonian matrix is nothing is on the imaginary axis. R, of course, is semi-definite. So then AR is stabilizable, it says, is equivalent to saying that that is in the domain of Riccati operating. Okay? So don't worry about this part. This is something we want to, because of the introduction of the special format of the H matrix, then we can make our conclusions much more compact. Okay. So the reason is we introduce this Hamiltonian matrix, and we can introduce something else, okay? Especially something called bounded real lemma. Bounded real lemma. So in that case, so you have A, B, C, D realization of the G, okay? So it is rational, stable, okay? Transfer function matrices. And you assume you have a scalar positive you want to tune, okay? You want to tune. And here, what you want to do is R square I minus D transpose D, okay? So you're giving A, B, C, D. Remember, you have A, B, C, D, okay? A, B, C, D. So what do you want to do? This is quite interesting. So you can see the expression is very compact if you introduce Hamiltonian matrix like this. So what you do is, you be careful here. All the R here, and here. Okay, it's a function of gamma. Okay, function of gamma. Okay, so if we can all this, if we have all these conclusions, they are equivalent. Okay, saying that how you can say the infinite norm of the whole G, original G, is less than gamma. So you change the gamma, your H will change, okay? You have to change. So based on the H, I change until I find the H has no eigenvalues on the imaginary axis, okay? So then this gamma is the upper bound of the infinite norm. This already points a numerical way to iteratively refine the G. Gamma until you see there's a eigenvalues on the imaginary axis. That's violates. Okay, so and the norm of D has to be less than gamma as well. If this is, it has to be less than gamma. Okay, if it's greater than that, so because this is direct transmission term. Okay, that's easy. Okay, so and the Riccati equation solution if the D is in the gamma. So all this saying is C is observable is equivalent to saying that Riccati equation has a positive symmetric solution. Okay. So you can say you can see introducing a Hamiltonian matrix like that, introducing this gamma in here, we'll be able to establish all this relationship, and there are two more, actually three more after this. So then that means, remember there is an ARE behind this one, right? There's an ARE behind this one. This is also true, I have an ARE behind this one as well. So this ARE will have positive definite, semi-positive definite solution X. And if the D norm is less than 1. Okay? But usually think about D0, okay? So it's automatically satisfied. Okay, don't worry about that. This is just for mathematically accurate. To see, you don't get bothered by this D. Okay. Okay. So you can see that everything is started to connect. So H infinite norm of the G, okay, is actually governed by, is related to the Hamiltonian's eigenvalue position. Okay, it should be half positive, half negative. If there is something on the imaginary axis, that means this is not true. Okay, so that means the gamma is too small. It should be bigger. Tune the gamma bigger. This is the same for the ARE. Okay, same for the ARE. Existence issue. And doing a lot of people doing RMI. So this is the starting point of RMI. Okay? I hope you understand. This is XA, AQ, AX, something is connected to the Lyapunov equation. Okay? But anyway, you write this 3x3 block matrix form. This should be negative, positive, negative definite. the whole thing is negative definite. So, but negative definiteness of this one is related to gamma as well as x. And x is also related to gamma. So you can always change the gamma, okay? So that this is negative definite. So this are all proved in our textbook. Okay. So this is already very positive, a very, very compact form to tell. So this is also called bounded real lemma. Okay? Bounded real lemma. So there are something they call this is standard ARE. You get ABC, then what we have. A B stabilizable, CA has no unobservable modes on the imaginary axis. So you always have a solution here. X is symmetric positive. If CA has no stable unobservable nodes, okay? So then this construction of H matrix is easy. Giving A, B, and C, you can always do this matrix format, okay? And how we can say that? It is because you can use the previous bounded real lemma. Okay? I don't think there are a lot of things left for you to prove. Okay, so knowing the results and the consequences and the meaning behind it is more important. We do have proofs. Okay. This is also similar to Riccati equation, writing B transpose and C transpose C, writing this one, then you will for sure have a unique positive semi-definite solution and stabilizing X. Okay. Meaning R is B times the gain X. Okay. So probably this ARE part is a little bit more abstract. The reason is we're not very familiar with the this H Hamiltonian matrix. Okay? Introducing the H Hamiltonian matrix will simplify a lot of presentations. Okay? And in modern LMI, people usually use this bounded real lemma. Let me show you. This is something we are going to use it a lot when you study the LMI. So this is a very familiar form. So the reason you feel LMI you are not very familiar with it is because of this bounded real lemma you are not very familiar with. So let's get this one started, H2. So we are now ready to talk about H2. And H2 is actually, we only have 6 slides on that. So let's start from the formulation here. And we have seen this one before. Okay? The A, B1, B2. I use a B11, B21. And C12, C21. Okay? And D11, D12, D21, D22. Okay? Okay, do you see that? I didn't give this. I removed this. They removed this one. If you have this one, you only have D1. Okay, and if you have Y, you don't have W. Okay. So they remove that. It's okay. It's reasonable. Okay. and they do C1, C2. So of course, you want to do stabilization, then what do? So remember, this is corresponding to Z. This is corresponding to Y, meaning Y equals C2X plus D21U. And this is Z equals C1X plus D12W. Okay? So this side is WU, this side is ZY. Okay? Okay? So, of course we need A, B, this is U, B1, this is B2W, so these are all stabilizable. Otherwise, you cannot make the system stable. What is the stabilizability? It's the controller subspace. It's uncontrollable, sorry. Is uncontrollable subspace is a stable space, right? If something that is uncontrollable, that is still stable, without control, then I said the rest will be stabilizable. The whole thing is stabilizable. If the uncontrollable part itself is unstable, then it will blow up anyway, no matter what control you do. Make sense? So this one is basically saying that unstable modes are stable. So uncontrollable modes are stable. Okay, stable. So uncontrollable modes, subspace is stable. Same thing is here. So C2A is detectable. So again, this actually are very weak requirement. Stabilizability is much weaker than controllability. Okay, controllable. Okay. So D12 column rank is unitary. What is this one? D21 full row rank. Okay. And this one you put A minus J omega full column rank for all omega. This is all this. So these are all assumptions based on controllability, stabilizability, observability, and detectability. Okay? So those are the assumptions. And what is the real H2 problem? H2 problem is nothing but exactly like what I said. I need TZW, 2 norm square. Without square is fine, but usually put square to be easier. Now what is here? My K, okay? I need a K. I need a K. My controller. What is my controller K? K is a transfer function matrix, remember? Okay? K is a state space as well, A, B, C, D. So in this case, we can say I have GCGF. What is GCGF? Okay. And you have F2 and G02, G1. What is this? Okay. We're going to see this picture in this way. So I need find a unique stabilizing controller K that can minimize that TZW. TZW is a 2 norm of input-output transfer function matrix, okay? Or complementary sensitivity function. Okay? So it turns out that my optimal controller, the solution of this one, is a realization of this one. A, B, and C, and D. We don't have D here, remember. And then A is none, B is none. I don't know F and L. C is none. I don't know F2. How to solve that? Okay. So So it's very complicated. So GCGF, what is GCGF? GCGF, you have A, B to F2. This reminds you F2 at the state feedback. Okay. This reminds you observer gain. Okay. So GCGF. Okay. So you have two ARE algebraic equation x2, y2, solving all of this ARE. And these are your state feedback gain, the solution of that. If you solve the ARE, you have x2. You have, these are all known. C, D, B, they are known. x2 is from here, ARE. Okay. Now error 2 is a gain matrix used in here. So what you needed is y2. And y2 is from this ARE. Okay. So you construct the state feedback controller in here. You have an observer like this. So this this is an H2 minimum. It will become GC times B1. F2. F2 is the gain. It's a matrix. It's a gain. F2 is here. GF is this transfer function. Okay. So that H2 solution needs two algebraic recurrent equations, okay? And so you may feel, wow, this is so complicated, how I can solve this problem? We know that the LQR with state feedback, you have estimator, okay, observer, then you have a state feedback. Okay. Here we have the same way, but it's more general setting. To solve this all stabilizing controller K, like we explained in last time, because if you are solving an optimization problem like this, see my mouse? And you want this K to be a stabilizing K. What you should do? Now we need to use that knowledge. It's called all stabilizing parameterization using Euler's idea to make that one happen. So how we finally end up with this one slide, this is a conclusion slide, this is the solution, problem and the solution, okay? He gave you that problem, gave you that solution, okay? But how you come up to that? So basically it's kind of interesting, okay? Our textbook has more details, okay? What they did is you have a control. So you have U, you have Y, you pull out this one. So you can see that we can introduce the parameterization using the Q. Okay? Don't get confused about this Q versus the previous Q. This Q is in a Q parameterization point of view. So the Q itself is any stable transfer function. Okay? So all stabilizing controllers can be parameterized in Q using the M, or M is this one. Okay, M is this one. Okay. Okay. So you close the loop, TJW will be written like this. So you end up with this one. So what is the unique optimal control K? Okay. Because Q is in here. You can change the Q, but others you cannot. Okay. So it turns out that you set this Q will give you this cost is smallest. Okay. That proof is also very interesting. Okay. Very interesting. We're going to continue on this one, and our time is almost up. I suggest you go to the textbook to see if we can follow this type of compact argument. I believe Kuminzo main contribution in this robust control H2, the derivation, is the introduction of the LRE operator, okay, Riccati equation operator, to simplify a lot of derivation, make things much clearer, okay, much clearer. We're going to continue next this Wednesday, okay, this Wednesday. So today you can catch me in my office. Probably not between 3 to 5 because I need to have another meeting. But 5 to 6 is possible. Okay. And any questions? I know H2 is a little bit off your mind, but however, stick with me. The H2 is basically a more general form of this picture. Okay, H2. I want to say that LQR is a special type of H2. Okay, special type of H2. Okay. So H2 is a more general setting, but this is already in the traditional case we learn all this thing. Okay, all this. Okay. Traditionally we learn all this. This is a state observer, but in our H2, we also have this structure. Okay, also have this structure. Okay. But remember, we're talking about H2 is because from W to Z. Okay, W to Z, and the W, we didn't say W is what. What if my W is impulse signal? Then we're talking about impulse response of the system, right? Okay. But what if my W is white noise? I didn't say that. What is my W yet, right? So H2 will cover much more scenarios. In fact, I want to say, H2 control combines LQR and LQG, because if you have a random noise, you want to minimize the output, that will lead you to LQG, right? Linear quadratic Gaussian. Okay. With that, you have the same structure here, but at that time, because of the filtering concept, we start to call this as a common filter. Okay, common filter. But that actually doesn't matter anymore. In the H2 is more unified setting, can cover both LQR and LQG. That's my understanding. I hope you agree with me. So here you didn't really say what is your W there. Okay. Okay. What's W? Okay. I think the W is a reference. It's all deterministic. Okay. So we don't have anything random. So that's why traditionally we need to learn LQR and LQG separately, okay, separately. But in H2, it can be unified as H2. Okay, that's all I can say. So learning H2, you are at a much higher level of abstraction. It's much broader applications. Okay. So H2 is fundamentally interesting because H2 is connected to the power, the signal power. To the power square is like energy, and you can say that. But in many cases, H2 may not be the thing we really want. So H infinity is something we really want. And another good news is when we learn how to use this H2 Riccati equation language, H infinite control will be much easier. Okay, much easier. So here is my suggestion for you to go back and check bounded real lemma, and it showed up in a very different forms. Okay, frequency domain, state space, and the connection. And you can see that bounded real lemma already give you a hint. What's the way to check the H infinite norm? And that one is the mathematical foundation. Okay? And again, I hope you review previous chapter regarding Euler parameterization, the structure here. Okay, structure here. And we're going to continue next week, next Wednesday on H2. I probably will run through an example to show you that the unification of LQR and LQG, and H2 is on the top. Okay? Okay? All right. See you later.